Welcome to ECEN 215 Principles of Electrical Engineering. The topic we are going to discuss is doing a review over some of the op-amp circuits we had in our previous topic, just running some example circuits and going over some equations, and introducing active filters and what those are about. So what we want to do first is build an op-amp circuit that implements a specific function. So we're going to do a couple examples like that, and then we're going to do an example where we're given a circuit and we need to figure out what the function is. So again, operational amplifiers are devices that actually implement mathematical operations. So let's go ahead and take a look at our first function that we need to implement. We have here we have V out, or the output of the amplifying circuit, is going to be 25 times voltage input number 1 plus 5 times V2 minus V3. So we need to go back and look at our amplifiers that we had in our previous topic, where we had different amplifier stages and what they are, and we're going to combine them to actually implement this function. Now, there isn't obviously a one circuit solution that actually does this, so we're actually going to have to cascade different ones. So looking at this, first of all, we notice that we have to first multiply. We're multiplying a gain factor, so we notice that. And we also look like that we're adding, and then of course we're subtracting. So we're adding V1 and V2 and subtracting out V3. So this is an overall a summation with gain. Now, given this, what could we use? Well, we had an inverting amplifier, and we also had a non-inverting amplifier. We had some that we had an integrator, we had differentiator, we had difference amplifiers, and we also had an inverting summer, which is good because the inverting summer, you can sum, up to n different stages. So that will take care of the V1, V2, and V3 summation. The only problem is it's a negative summation. So it's basically V out would be equal to minus V1 plus, or it's with some gain RF over RN for that stage, V1 minus V2 minus V3. So it's summing the inverse of the inputs. But that's useful because if we put an inverting amplifier in front of that, we can flip the mathematics around. So the first thing we need to do is set that up. So we're going to go ahead, and if you notice, we've got two that are positive here. So let me highlight that. So we've got two here that we're going to be multiplying by gain of 25 for the first one, plus 5V2 minus V3. So what we're going to do here is we're going to use an inverting amplifier, and then in the final stage, we're going to use an inverting summer. So let's go ahead and implement that. So our first thing is our first stage is an inverting amplifier, and we're going to focus on input for V1. So this is going to be V1. Now V1 is going to have a gain of 25. We're multiplying by 25. So we could use, just so that we have some reasonable impedance, we're going to use 25 here, kilo ohms, and we're going to put a 1 kilo ohm resistor here. All that matters is the ratio, because remember, for an inverting amplifier, V out over V in is equal to minus RF over RN. It's all about the ratio. Here we got 25K, that is our RF, and our RN is 1K. So 25 over 1K, 25K over 1K is 25. And of course this minus, so the output of this is minus 25 V1. Now let's do the same thing for V2, and you're going to see how this connects together in a moment. So we have V2 here. We're going to use an inverting amplifier, and we're going to put V2 as the input. And here we're going to do 1K for the R input, but over here we need 5. So we're going to put 5 kilo ohms as our feedback resistor. Again, minus RF over RN leads us to minus 5K over 1K. So now we have the output here is minus 25 V1, and the output here is minus 5 V2. So that's our output here. Now the other one is just simply a gain of 1 minus V3. So now let's just completely separately over here, let's implement an inverting summer that sums 3 inputs. So here we have, it doesn't matter what these resistors are, they can be all the same because in the end, we need a gain of 1. So we're going to just set these all to 10 kilo ohms. So the overall gain of this amplifier here is minus RF over RN. And if these all happen to be the same, that's the same gain for each stage. Now you can have a separate gain that's RF over this particular resistor, so you can have one gain here, another gain, and you could have done this amplification of 25, for instance, here in this stage as well. And the output of these right here could have simply just been a gain of 1. So again, there's multiple answers to this. So we could do this. We have RF over RN, where this happens to be 1, and it's V1 plus V2 plus V3, where this is input 1, input 2, and input 3. Since we're all doing the same gain, and we only needed a gain of 1 here for V3, then we simply just need to put V3 here. And if we go ahead and connect this here, and we go ahead and connect output number 2 here, what we end up with is a combined equation that's minus RF over RN, which is minus 1 times V1 plus V2 plus V3 of this part of the stage, right? But V1 here, in fact, I'm going to go ahead, I'm going to call this VA, VB, and VC, just so we can designate this as a separate stage. In fact, we'll go ahead and we'll leave this V3 because that truly is our input. So, but VA is equal to minus 25 V1, and VB is equal to minus 5 V2. So substituting that into this equation here, we end up with minus 1 times minus 25 V1 plus a minus 5 V2 plus V3. But we got to carry the minus 1 through, and so we end up with our final output equation, V out is equal to 25 V1 plus 5 V2 minus V3. Okay. So now let's do another example. So we're going to implement a function, build a circuit that implements 10 times V1 minus V2. Well, this one's straight out of what we looked at before. This is just simply a difference amplifier. All we have to do is multiply gain of 10 times V1 minus V2. So pulling that slide, we have this. And so all we need to do is, of course, we're going to make it where the ratios here of R4 over R3 is equal to R2 over R1. And if we do that, then we just need to simply make this equation work for our goals. So V1 is V1, so that one's easy enough. So V1 will go here, V2 will go here, just as it's implemented here. And so the only thing we need to figure out is what the ratio here for the gain, 10. So if we choose this to be 10 kilo ohms, and for that matter, this happens to have to be 10K, then correspondingly, if this is 1 kilo ohms, then we have our solution. We have 10K over 1K, which is equal to 10, and then we end up with 10 times V1 minus V2 as the output. For this circuit here, we need to implement is simply 10 DDT of V1. So if we go back and look at the different circuits we had in the previous topic, we actually have everything we need. We have a differentiator and we also have an inverting amplifier, because the resulting here, the differentiator was minus 1 over RC dt of its input voltage, which is an inverting version. And since we don't want to invert, instead we want to actually have a positive gain, we're going to need to put an inverting amplifier. We can put it either on the input or put it on the output. You can swap the input and the output, or the stages. You can have stage 2 be the differentiator and stage 1 be the inverting amplifier, or vice versa. It does not matter. So to do this, what I've decided to do is I'm going to first invert the input and actually apply a gain, and then push it through the differentiator with a gain of minus 1. So we're going to have first an inverting amplifier. And so just as a refresher, the stage here this is RF, and this is RN, and this is V1. The output here is minus RF over RN times V1. So that's that. And so let's go ahead now and take a look at the next circuit, which is the differentiator. In this one here, we're going to put VA here, just so that we don't confuse it with V1. And the output here is minus 1 over RC dt of VA is equal to V out. So that's what this stage is. So first thing we're going to choose, I want this to just be go ahead and this part here just be equal to minus 1. So to do that, what we're going to do is set this to 100 kiloohms and this to 10 microfarads, which gives us minus 1 over R times C equal to minus 1, which is exactly what we would want. Okay, so now what about this? Well, this, correspondingly, we need this output in the end to be 10, so we're going to want RF to be equal to 10 kiloohms. And therefore this needs to be 1K, leading to a gain of minus 10K over 1K here times V1, and of course this is connected to here. If we do all of this, then V out is, we'll just write it out piecewise here, is equal to minus 1 over RC times d dt of this being minus 10K over 1K times V1. Since this is a constant, then V out can be simplified as equal to minus 1 over RC times, in this case, minus 10K over 1K times d dt V1 of t. And since we chose RC to be equal to 1, we end up with V out is equal to minus 1 times minus 10 d dt V1, which in the end is just simply 10 d dt V1 of t, which is our goal. Now the question, we're going to flip everything around. We're going to actually give a circuit, and we're going to be asked what is the gain or what is the output function of this circuit. So this is simply an integrator circuit combined with a non-inverting amplifier. So what you have to do here is do each part in stages. So again, this one here is just simply minus 1 over RC, the integral of 0 to t, t being time, of Vn of t dt. So that's this stage. This is the output of this particular amplifier. This one here, right here, is got a gain that is equal to 1 plus R2 over R1 times its input here, which we'll just call VA. So we have that. So this here obviously is at the same time is equal to VA. So our total gain, which is also known as AV for this circuit, is what we have minus, because it's still got the negative, 1 plus R2 over R1, because we're just going to do this in terms of the elements. We're not having any values specifically. So 1 plus R2 over R1 divided by the RC that is over here. So this is our R1 and R2. So that's our overall gain of the function. And then it's just simply 0 to t Vn dt. And that's it. All right, so now we're going to talk about active filters. So we've been looking at all these different op amps, and we have had a introduction to frequency response, and we talked about two-port filters before where you have resistances and capacitances, and you can also do the same thing with inductors, for instance. But an active filter involves using one of these RC type filters in combination with operational amplifiers. And there's various reasons why you're going to want to do this. Because one of the things you probably have noted is by using an RC circuit, if you do cascaded filters where you have filter 1, then you got filter 2, and you got filter 3, filter 4, filter 5, it all depends upon those elements. And as you've known by doing circuit analysis, when you start combining elements together, the overall impedance of them is based upon the total equivalent impedance. There's nothing separating the stages. So you can end up with some kind of odd interactions in combining the stages instead of being simply just the transfer functions multiplied together. So one of the primary, so these are the actual reasons why you would use an active filter, specifically in the case of where you would be using this in your discipline in the future. First of all, you would have a case where you have some sort of a sensor signal and it's got noise for whatever reason. There's lots of noise that's generated by power lines. There's noise that's generated by fluorescent lighting, or there are high frequency filter or noise sources that are caused by motor controllers that are done because we're using one thing known as pulse width modulation a lot of time at a very high frequency, usually in the tens and hundreds of kilohertz. And so all of these kind of noise sources can sometimes end up getting superimposed upon a sensor signal like a strain gauge or temperature or pressure, so on and so forth, of a mechanical system that you're actually trying to measure. And as such, you want to actually filter out some of these higher frequency noises, especially if your signal is needing to be low frequency. You can also have to have the need where you're going to have to do, say, a band reject filter and specifically get out certain very specific signals. For instance, sometimes it's real common to use a 60 hertz band reject filter to get rid of if there's a lot of power line noise that's coming into a signal, you can actually put a 60 hertz power filter to reject the power line frequency. Or if you're getting specific radio interference, if your circuit is for whatever reason very susceptible to cellular band radio frequency, for instance, and it's causing problems with whatever signal analysis and processing you're doing, then you sometimes are going to need to have a specific band reject filter for that. You might be, in this case, you could be specifically targeting specifically frequency range. As we were talking about in the frequency response lecture, you have different frequencies of interest. For instance, electrocardiograms, audio frequencies, things like that. Or you're specifically looking for a radio frequency. And so you would specifically target a frequency range and build, in that case, a band pass filter, which will only allow the frequency signals of interest that you want. There's something known as an anti-alias filter for your analog digital converter. That's just a fancy phrase for a low pass filter. If you use an analog digital converter, and we'll be talking about this in the microcontroller lecture a little bit as well. Um, when you start, nowadays, in the last 20 years, embedded systems have kind of become a forefront, and pretty much almost all signals nowadays are sampled by an analog digital converter so that you can actually do computations digitally upon the data you're receiving. As such, if your frequency of sampling the data happens to be, say, 1,000 hertz. In other words, you're sampling the input filter or input signal at 1,000 hertz, then you're going to want to make sure that whatever signal is coming in is no faster than about 500 hertz. Because if you do that, you'll end up with something called an alias. An alias is something that is basically a figment of the fact that you are sampling too slow. You actually see this every time you watch a movie or even as you're watching vehicles drive down the road and it looks like wheels are going backwards. That is because of a thing, alias. Your eye is actually sampling the visual activity that you're seeing slower than it is actually rotating. Another common thing is if you ever used a timing light to time an engine, the timing light actually is set to the frequency of the rotation of the engine. So if your engine is rotating at 1,000 RPM, the timing light is firing at 1,000 RPM, and it makes it look like the flywheel on an engine is standing still. And as such, you make if it's not standing still, you have to make slight adjustments to kind of raise it and back it off and things like that. So you're actually, you know, seeing it stand still. Now, in reality, it is not. And of course, things can be very dangerous if you think the engine isn't moving and it actually is, and you reach your hand down there and try to touch the flywheel, and you're going to learn real quick it's actually rotating at 1,000 RPM. But visually, it is standing still, and that is because of a thing known as alias. So you have to put a low pass filter in front of your analog digital converter to reject or get rid of these high frequency signals. Else you end up receiving something that maybe looks like a real signal, in which case it's actually fake. And that can cause all sorts of problems in embedded control systems. So you basically put low pass filters on your analog digital converter. And as such, you can also, on the other side of this, you have a digital analog converter. I want to control something, make some computations, and then try to control an output voltage or an output current going to a valve, for instance, a proportional valve controller. Then you're going to want to also put a filter on the output so to get rid of any high frequency noise that can come from those computations or anything that's happening in the circuit, because the filter, or not the filter, but the output stage or control element is not going to really respond as fast as you're updating it. So you're going to want to smooth that out. And then another reason you're going to want to use an active filter is also to increase the gain for specific sensor input. Sometimes a lot of sensors are really low signal and you have to amplify it. Well, if you amplify the signal, you also amplify the noise. And the noise usually is a higher frequency and is not maybe a low frequency actual signal. Maybe the signal that you're looking for, say a position of an actuator, so on and so forth, is maybe 10 hertz or even in the hertz realm. But the noise that's being amplified is usually going to be in the hundreds of hertz, if not kilohertz range and above, and as such you're going to want to amplify, but yet at the same time put a low pass filter in there to reject that noise. So some of the ideal properties of an active filter is that it contains minimal components. The idea is you want to make a strong, good filter, but you want to do it with simple handful of parts. You don't want a complicated filter with, 10 inductors and capacitors and resistors all over the place. You want something that has minimal components and that the transfer function is insensitive to those component tolerances. As you've learned in the labs, there's tolerance to resistors. When you tell something that's 10 kiloohms, well, when you buy the resistor, it's 10 kiloohms plus or minus 5%, or it's plus or minus 1%. Of course, as you want a tighter tolerance part, the cost of the part goes up. So you can get down to like 0.01%. You can get a really accurate resistor, but you're going to pay for it. So you want to try to make sure that the transfer function of your filter is insensitive to those minor changes in tolerances on the components. You want to make sure that it is effectively using op amps, because op amps, as we've learned, are a very powerful integrated circuit. They allow us to isolate different, in this case, going to be different filters in different stages. So they're really great. They have an infinite input impedance and they have near zero output impedance, and ideally, so they're great. But at the same time, there are some limitations. There's limitations on the gain. There's limitations on the what we know as the bandwidth product, what is the frequency range. So the nice thing about active filters is you want to make sure that ideally that you use the op amp correctly. Nice thing also about ideally with active filters is that they can be easily adjusted by simply changing a resistance or a capacitance value. You can simply change the cutoff or cut on frequency for an active filter. And of course, another ideal property is it requires a small spread of component values, meaning that you don't have to have a large capacitor, something that's in the hundreds of microfarads, thousands of microfarads, and have something in the mega ohms. You can kind of keep the values of the resistors and the capacitors in a reasonable range that are effectively purchased, they have tight tolerance, and that they can fit on the circuit board. That's a lot of the advantage of active filters, and that's mainly driven by the properties of the operational amplifiers. And the last one is the fact that it really allows for a wide range of transfer functions to be realized. Again, one of the main advantages of operational amplifiers is they implement transfer functions. You can implement mathematical functions. And analog control, before we really got into the realm of digital control, was all done with operational amplifiers. So if you were doing a control function to actually control feedback of, say, of an actuator or a control valve of some kind on a control plant, you would actually could implement this using an active filter and build a transfer function. So if once you finally take a controls course in your discipline, which is possibly likely, then you would actually see that active filters can actually implement those transfer functions that you come up with. So let's take a look at some active filters. So this is the whole purpose of this lecture here is just really to introduce you to active filters and let you see what they look like and how they operate. There really isn't anything that's per se that's going to be really covered in any depth here. It's just really to give you an overall view and taste of what active filters are about. So here is just a simple low pass filter. Obviously, you've seen this before. This is just a low pass filter here, and this is just a resistor capacitor like you've seen in the previous lecture on frequency response. And the only thing that we've done differently is we have put a non-inverting amplifier on the output stage. The advantage of this is no matter what type of load we stick out here, it is isolated from this filter. So we're not affecting the current draw and affecting basically the output stage of the filter just based upon the load, which is if you use the standard, if you go back to the frequency response lecture and you actually use a low pass filter out of there, it can complicate things because now as you put a different load resistor or something here, you're actually going to change the effective cutoff and cut on frequency on the filters. In this case, you would change the cutoff frequency and actually cause it to shift. Well, that is not the goal. The goal is to simply have a resistor and a capacitor that's set. That is our frequency, and no matter what load I stick out here on V out, it is consistent. So looking at this, the output frequency is simply, the AV is the gain of the DC gain of the amplifier. In the frequency response of this, normally this was 1, but now it is 1 plus R2 over R1, just simply the DC gain of this amplifier here. And it's over the low pass filter, which is 1 plus F over FC squared. So this here is the equation that we had in the frequency response lecture, if you want to review that, to how we achieve that. But this is the gain of V out over Vn, as AV is equal to 1 plus R2 over R1 divided by the square root of 1 plus F over FC, where FC is just simply 1 over 2 pi R3 times C1, this right here. And just looking at this, if for instance this output gain was 20 decibels, which remember this would be 20 times the log of V out over V in, so this would be a gain of 10. So if you had this, you would end up 20 decibels, and at the cutoff frequency, it starts rolling off. And it slopes down at, basically the roll off is 20 decibels per decade. Correspondingly, we could flip the circuit around, change the position of the capacitor resistor, and now the very same filter can be used as a high-pass filter. So if we do that, we end up with this as our transfer function, 1 plus R2 over R1 multiplied by F over FC. So this part here is the high-pass filter transfer function, and it's just being multiplied by our R2 over R1 equation for a non-inverting amplifier. So same non-inverting amplifier's gain section, but we've just changed the filter on the front end. Now, again, the advantage of this is no matter what the load is, we are now isolated. Now, of course, you can even put another amplifier stage here on the front end. You can put a buffer amplifier, so it truly isolates the filter section from any input-output effects. And of course, it has the exact same, in this case, cut-on frequency of 1 over 2 pi R3 times C1. So there is a gentleman named Stephen Butterworth back in the 1930s came up with a set of transfer functions dealing with low pass and, for that matter, high pass filters. This is known as the Butterworth transfer function, and it's just various things dealing with these orders. So we've been looking at an order of 1. So if you notice, an order of 1 has a very slow roll off, of 20 decibels per decade. Now, that's usually fine for a lot of functions where you don't really care. You're just trying to get rid of general noise and things like that. But sometimes you're going, like, especially if you're doing band reject and band pass filters, you're wanting to create a roll-off that is really steep so that you get to the frequency of interest and it turns on, and you get to, like, if you're doing a band pass, it turns on and then it turns off. You got a real narrow band and it's really sharp. That would be the goal of that. And in that case, you're actually going to want a higher order, but that kind of complicates things. So he came up with this a transfer function that had a transfer of magnitude that was some gain here H naught, and it just simply, as the order increased on the factor of n, this just got stronger and stronger, this F over FC, so it just became sharper and sharper as it went. So this, as you increase n, it just rolls off faster and faster. And for instance here, n is equal to 4, and you can see we have a really steep roll off. H naught is known as DC gain. It means that at the gain of, like in here, 1.0 of 8 magnitude over H naught, 1.0, it's like this. If you want the DC to be gain in the previous example that we were looking at a moment ago where we have, say, a gain of 10, then that would be H naught. And then that would just be divided, of course, by the transfer function part related to frequency. So the DC gain is your H naught. N is the filter order. So what we have here is we have an actual implementation of the Butterworth filter. Now, when Stephen Butterworth came up with the filter concept, the idea was this was done in the days of radio technology, was a prevalent thing, but this is even before television. And he was trying to come up with transfer functions to allow, if you will, creating bandpass filters to filter out certain radio, stations, basically, or carrier frequencies. So the tighter your transfer function, the tighter your filter, the more accurate you could be at just isolating the radio station of interest. Now we are just going to implement those transfer functions with an operational amplifier. This is known as the Solid Key Active Filter when you do that. Notice the fact that we have a non-inverting amplifier as before, and the transfer function, similar to what we were just looking at, is H naught over 1 plus square root, the square root of 1 plus F over FC 2 to the n, where n is our filter order. And of course, with this, we have 1 plus R2 over R1. This is a non-inverting amplifier, which leads us with this this resistor here is just magnitude difference of K minus 1 multiple of RF, with the RFs cancel, and then this 1 and this minus 1 cancel, and you end up with H naught, or the DC gain is just simply K. And of course, the same applies. So we have our R and our C here, and the cutoff or called on frequency. If this was you can flip the resistor and capacitors around, and you can turn this into a high pass filter. It ends up being 1 over 2 pi RC. So that's just a good point here. If you wanted this right, this is a low pass filter, but if you wanted to turn this into a high pass filter, you just change the resistor and the capacitor locations, and it flips. As such, the filter order again is N, and the number of stages is equal to N divided by 2. So this right here being one stage gives us an order of 2 filter. So if you want to have more stages or more order, then you just have to add more filter. And of course, it's an even number of orders. So 2 stages will give us an N of equal to 2. So here are some of the common values of K, depending on the order that you're interested in. So for instance, just an order of 2, one stage, typically you use something about 1.586 as your gain. Order of 4, a 2-stage set, you have a couple different values. This is just what is recommended. You can play around with these values in MATLAB or a filter designer, but these are just some that are recommended for the K values for low pass to high pass Butterworth filters using the solid key configuration. So here's just another example of simply a multi-staged solid key. So this is a 2-stage, which means what? That means we have an order of 4. So here we have H naught is K squared. And the reason that, remember, amplifiers cascade, meaning that everything multiplies. So the gain of one is equal times, the output of that is then multiplied by the gain of the next stage, so on and so forth, as we were just seeing with the earlier examples. So if both of these are identical circuits, everything is the same. All the components are about the same value. They're all at the same value. In other words, minus tolerance changes. These are exactly the same circuit. That means this has a gain, a DC gain of K. This has a DC gain of K, so you end up with K squared. So you can imagine if this was, you had 3 stages, then H naught, or the DC gain, is just K to the number of stages. So if you had 3, it would be K to the 3. So your DC gain is just K times K times K times K times K, depending on the number of stages. Again, the advantage of this is now we're going to end up with a very sharp filter response. So in this case, K, let's say, is 1.52, which gives us an H naught. So if we chose our K value here to be this, arbitrarily we just chose this value on that table we looked at a moment ago, then H naught is just simply 1.3271. And of course, the FC is the same for both. The same cutoff frequency, for being that this is a low pass filter, is the same. And this gives us an N equal to 4. Therefore, we have, this is our transfer function. So this is our Butterworth 2 to the N. And as such, we go back to the graph we had a moment ago. And now we're N is equal to 4. So you notice we're very sharp. Of course, we could have done N equal to 8, and it would have been extremely sharp. But N equal to 4 is good. It's just simple 2-stage, not a lot of components to implement this. There's a very sharp cutoff, so this is very effective in using as an active filter, as a high frequency, or a high pass or a low pass filter, or you're thereby creating a band pass or a band reject filters. You can use these in that configuration by just changing where your cut on and cut off frequencies are located. Now, the interesting thing here, we have N is equal 4, is this flat band. If you dig into other types of filters, and there are various different kinds, sometimes the pass band, as it known, which is this part here, is not flat. Sometimes it's very ripply, but they have very sharp cutoffs. So if you're really not caring if your amplification is perfect here, but you're wanting a really sharp cutoff, ideally, obviously, you would want it to be right here at 1.0 just to be completely cut off. Then there are different transfer functions for that, but they don't have as flat a pass band. The nice thing about the Butterworth is the pass band is very flat, allowing the signal that you're actually receiving to be of quality, and that you can trust that it is going to be the value you're reading. And of course, the interesting thing here is that in the case of decibels, the roll off originally, per order, per N is 20 decibels per decade. So here it's 20 times N. So if your roll offing is minus 20 decibels per decade, then it's minus 20 dB times N. In this case, N is equal to 4. So it's minus 80 decibels per decade. So last thing I wanted to state is that active filters, we just kind of get as long as this actually has been, we've only really have touched the surface of active filters. And again, this is not a class on active filters, and this whole point is just to kind of give you a flavor of this concept and the usefulness as such. There are dedicated books, as you here, this is out of my personal library, just a couple of the books I have. I actually have about 5 or 6 books on active filters, and because there's a lot of different reasons why you would use active filters, and as such, a lot of these have been pre-designed. These books are actually quite old and have been around, and the circuits and the concepts have not changed over the last 30, 40 years. So they're very stable, they're very high quality, well known, and so having some active filter books is useful if you're going to ever implement this and you're ever going to be involved in any signal processing in your discipline. So in summary today, we did various examples of operational amplifier circuits where we were given equations and we had to build the circuits, or we were given an equation and we actually had to, or given a circuit and we had to come up with the equation. We looked at active filters and what they are, what they means. We looked at a low pass and high pass first order active filter. We looked at Butterworth filters and the transfer functions thereof, and we also looked at Sollen-Key active filters, and specifically the Sollen-Key low-pass filters and fourth order double-stage Sollen-Key